So now we have described our interactions between mapping and statistical workload density model, and what the interaction tell us is essentially the statistical characterization of the fiber occupancies. They tell us what is the sparse nature in a statistical way for all of the fibers involved in your tensor. So now we're ready to take the second step, which is to analyze the interaction between your defined statistical characterization of fiber occupancy and the actual sparse optimization features. So let's take a look at how these two interact with each other. Okay, so again, as we have already said, we have already defined. You can imagine that we processed the mapping and the statistical workload, and we have defined the statistical occupancy of a fiber. So after the definition, our fiber will have some non-empty fiber elements, meaning in the original tensor, these elements are non-zero. And we will have some empty fiber elements, meaning the original tensor, these elements are actually corresponding to zero values. And both of these elements can be accessed, and we classify the type of accesses based on whether you're accessing a fiber element which is non-empty or a fiber element which is empty. So let's look at a simple example to see how does this access classification work out. Again, we're looking at a simple workload, which is a dot product of vector A and B with the dimension of k. Let's look at A. Let's focus more on the A tensor because we only want to define how these access types happen. So let's look at A only, ignoring B. So we would have the fiber tree representation of A in this format because we have 3 non-zero values with coordinate 2, 3, and 5. We will also be able to represent A, and let's focus on the default uncompressed A representation for now, which is essentially a payload of A with all of its values. So how do all these different types of access happen? Okay, now, so let's look at how in hardware we're accessing this payload A, and then we'll see how these different accesses have happened during this process. So we have this main memory which stores the A payload, and we want to look at the accesses to the storage across different cycles. The first cycle in this workload will essentially access the first A value in the payload vector. Remember, this is default uncompressed, so we will access this 0 value, which is in the position 0 of a P vector. And I have put the classification of access types here as well. So the read of the first element in A payload is an access to an empty fiber element because originally this element is not present in your fiber tree, right? So it's an empty fiber element, and this read belongs to this category, which is an access to empty fiber element. The second read is the read to the second position in the A payload vector. Again, because your second position has a 0 value, which is not present in your fiber tree representation, this access is again a access to an empty fiber element. And the third access is not different. It's an access to the third element in the payload of A, which is the C value that we see here. And because the C value is non-zero, we are performing an access to a non-empty fiber element which is present in our A fiber tree representation as the first coordinate in the fiber. So we record the read of A payload third position as an access to the non-empty fiber element. And similarly, you could look at the fourth position, the fifth position, and the last position in A payload vector and classify them as different types of accesses and as shown in this figure. And as a baseline, we are having 6 actual accesses to the vector, and there are 6 cycles. So now let's see how our sparse optimization feature can play a role here. So sparse optimization feature essentially impacts the number of accesses that we looked at. So it reduces the actual accesses into different types of other types of accesses, and the first type is the gated accesses. And the gated accesses is caused by the gating optimization. Recall that gating is explicit energy saving of accesses to the payload of one element of a fiber based on the emptiness of an element of another fiber. So it is a condition on situation where if you see that your corresponding operand is empty, you don't read yourself. And one note here to pay attention is for simplicity, we can now treat payload as the exact value, but you could imagine the payload as a fiber or a tray of fibers. So you could actually eliminate more of your fiber tray with the gating optimization. But for simplicity, let's just treat the payload as a value as the first step. So essentially, you're eliminating the rate of a specific value in your tensor by looking at another one. So let's look at an example to solidify this idea. So again, we have this workload, which is a dot product of vectors A and B with dimension k. Again, A is stored in the main memory, and we again only care about the tensor the accesses to a tensor. Let's imagine that we're able to tell which value in B is 0 in some magical way. So you could have different ways to figure this out, right? You could actually read the B vector to figure out, or you could have some additional information in your B representation so that you know which location your B is 0. But let's treat that as a black box for now, because gating doesn't really care about how you are able to tell that which location in B is 0. So we know which location in B has a 0 value, and we want to gate A based on B. And we represent that with this purple gating unit below the main memory. And this is saying if the corresponding B value is 0, we want to perform a gating optimization on A. And let's see what happens. So in the first cycle, the rate to the first element in A payload vector is gated. The reason is because we know that the first element in B vector, which is the corresponding operand to the first element in A, is 0. So this operation is gated. And recall that gating only causes an idle hardware component. It doesn't reduce the number of cycles. So the first cycle is still spent. However, we are spending an idle cycle because the fact that B has a 0 value. We have to read the payload of A1 and payload of A2 because the corresponding B value are also non-empty. We have then to read. We then don't have to read the next value of A, which is the D value, because you are then able to know that B is empty at the corresponding location, so we don't need to read D. And you probably have also noticed that during our second cycle, we're reading AP1, and AP1 is actually an empty element. We are still reading it even if we're applying gating optimization, and this is exactly what it means by we are gating A based on other tensor's 0 emptiness instead of its own emptiness. So because in the second cycle, B has a non-empty value, even if A is empty, we have to read it out. Okay, so second and third cycles are read out, The fourth cycle is gated because we have a 0 value in B vector. The next cycle is also gated as we have another consecutive 0 afterwards, and you can see we're updating the different access types as well on the right. So because we're gating in these two cycles, all the corresponding reads are classified as gated accesses. And again, we'll have to read the last A value because our last B value is not empty. Gating will say that the tensor that you want to look at is not empty, so you have to be reading your last element out. Okay, so as you can see in this example, gating is able to save number of accesses. So recall that we have a number of actual accesses of 6 in our baseline. Now it's reduced to 3. However, the number of cycles spent is the same because gating doesn't save cycles. The next optimization is skipping. Skipping is the explicit elimination of accesses and computes based on, again, the payload of another element in another fiber. And as you can imagine, skipping also leads to another type of access, which is the skipped access. So let's look at an example as well. So again, it's the same workload. It's a dot product of A and B, and instead of gating, now we're applying skipping to this main memory block. Let's see what happens. So in the first cycle, we know that the first element in B is 0, and because we're applying gating, we will proceed to the second element of B. And we realize the second element of B is non-zero, so then we'll read out the second element of A, which is AP1, the second element in the A payload vector. We'll read out in the next cycle the third element in the A payload vector because the corresponding B value is not empty. And we will then look at the next values in the B vector. We realize that the next two values are both 0. So with the skipping optimization, we can then directly skip ahead and read the payload of A, read the last payload of A. And again, you can classify the different action types as shown in this figure. And because skipping allows us to actually skip cycles, we have reduced the number of cycles spent as well. So we have 3 actual accesses as what happened to the gating optimization case, and 3 cycles because of skipping optimization. Okay, so now we have reached the last type of sparse optimization feature, which is picking the data representation format to save storage space, and also allow the reduction in storage accesses because you are not storing the 0 values. And this will lead to the elimination of the empty fiber elements because you have now said that all of these elements are empty. I have already let you know that these elements are empty, so you don't need to access them. So all of the associated accesses to the empty fiber elements will be eliminated. So let's take a look at an example. This is a simple traversal of tensor A because really when you're picking a compression format, it doesn't matter what the other tensor is represented in. So we are only looking at the tensor A and we are looking at the traversal of it. And as you can see here, we are representing A as a coordinate payload list. So since A has 3 non-zero values, we have 3 payloads C, D, F, and 3 coordinates 2, 3, 5 in our data representation. Because we have chosen this data representation format, we have then to both store the payload and the coordinates of A in the main memory. And this is what it means by AC and AP main memory block. And this icon means picking a data representation, which is coordinate payload. And it's very simple in terms of traversal. We're essentially reading each coordinate and payload pair out of the storage so that we know both what it is the non-zero value as well as where it sits in the original tensor. And this optimization reduces the number of actual data accesses to 3, and we only need to spend 3 cycles because we don't really have all these zero values stored anymore, so of course there is no cycle spent for these 3 zero values. You probably have also noticed that we have 3 extra accesses, which is to the metadata stored in the storage. So this is exactly what happened with this kind of data representation choice. By choosing a data representation format, you are essentially incurring overhead, both in terms of metadata accesses as well as metadata storage. So let's take a look at a high level of how do we analyze the amount of overhead associated with metadata, and also actually how do we represent or what data representation format are supported here. So essentially metadata allows us to identify the location of 0, and they're necessary for implementing a lot of sparse optimization features. So here we're essentially showing the different data representation formats supported by us. So you could have bit mask, which uses 1 bit to represent whether the specific location in your tensor has a 0 or non-zero value. This bit mask representation can be compressed or uncompressed, where compressed bitmask only stores the non-zero payload, but uncompressed bitmask stores all of the payloads. You could also have offset pair, which is the CSR upper rank. So you're basically telling us how many zeros or how many non-zero values there are, where they are storing in the memory by using this metadata information. I think we already have gone through this in very much detail in the first section, so I'm not going to spend a lot of time on this, but this is essentially telling us where is the corresponding non-zero values stored for the specific coordinates. We could also have coordinate payload where we're actively listing out the coordinates associated with the payload. So it's, for example, 235 as explicit coordinates. We could also have rank length encoding, which is describing how many zero values there are before this non-zero value, or between this non-zero value and the one before it. So all of these data representation format can be applied to the ranks of a tensor, and internally we could analyze how much extra space does it take for us to have these metadata stored or associated with a specific tensor. For some of them, we are able to derive the extra accesses and extra storage overhead by looking at the shape of the fiber, because as you can see, all of these 3 representation format is not associated with the non-zero values in the fiber. It's only associated with the shape of the fiber, and the others are more related to the fiber occupancy, because we are, for example, for coordinate payload, we're only specifying a coordinate if you have a non-zero value there. So the analysis then associated with these kind of formats are more dependent on the fiber occupancy, and as you can imagine, then the overhead of metadata becomes statistical and is dependent on the density model that we have chosen. And of course, you could have tensors with multiple ranks, and here we're I'm showing an example of a tiled tensor A, and because of the tiling, you would then have 2 ranks for this tensor. And as described in the first section of our background lecture, you could represent a compression format or data representation format for multi-rank tensor by specifying the format for each rank. So as shown in this figure, we're able to specify the format for rank M1 and M0, and we're able to freely choose from these options that are available as we just described. And as you can imagine, in order to evaluate the overhead associated with a multi-rank tensor, you have to go rank by rank. You have to look at the statistical occupancy of fibers in the specific rank if needed, the number of fibers in a specific rank if needed, and then you will be able to derive what is the cost at each rank, and the aggregation would be the overall cost of a tiled or of a multi-rank tensor representation. Okay, so since we have seen simple standalone examples for these sparse optimization features, we could also take a look at some simple interplay between different sparse optimization features. And at a high level, what this means is essentially you could apply different sparse optimization features to the same component in the architecture. And all of these different sparse optimization features can have different impact, and all of these impact will then aggregate for the component they are applied on. So let's look at an example to see how this works. Again, let's have a dot product workload of a vector A and a vector B with dimension k. We have a shorter vector just to make our example simpler. And we have now chosen the data representation for both A and B. And this is what one of the sparse optimization features, which is the format choice, right? So for A tensor, we are choosing the coordinate payload representation. For B, we actually didn't apply any optimization, it's still uncompressed. And we want to do some optimization like this. So basically, we want to look at the coordinate and payload in A, and we only want to perform an operation, a multiply accumulate, which is the operation, when we have the A payload present. So as you can see in this for loop, we're picking out the coordinate and payload from A, and we're only performing a computation if there is a payload. So this kind of optimization can be realized in this way, right? So when we have the A and B information, we could apply a skipping of B based on A. So if your A is 0, meaning if your A is empty, then you don't read B, you fast forward to the next B that's needed for computation. And because of the representation that we pick for A is a special representation other than default and compressed, we're also applying a format optimization, and the format is coordinate payload. So let's see how it works by looking at what happened at each cycle. So in the first cycle, we first read out the coordinate of A, and we realize the coordinate is 2. And because we have this skipping optimization on B, which says if the corresponding A element is empty, you try to read the next, or you try to find the B element that actually makes sense, which means a B element that is used for a effectual operation. So in this case, we realize the first effectual operation is at coordinate 2. So then we fast forward for 2 B accesses, because the element 0 and element 1 are both corresponding to a ineffectual computation. So then we directly fast forward by 2 accesses, and we access the third element in B, which is BP2, and of course we'll need to read out the payload in A. And essentially we're reading out the C and I element from A and B, and then you can imagine we can do a computation with C and I, and also we will then read the next element in A, and this time it is the very adjacent element D to C, so then there is no fast forwarding needed, or there is no skipping needed for B. We just sequentially read out J, and D and J will allow us to perform a effectual computation. Let's have some assumption of A coordinates payload and B payload. Let's assume that we have a pretty light coordinate metadata overhead with only 2 bits coordinate values, and our data payloads are all 8 bits. So this optimization you can calculate if you want, but essentially this optimization allows us to reduce processing time by 2x comparing to baseline. It allows us to reduce the hardware capacity requirement because we didn't store the 0 values of A, and because the coordinates metadata is less significant comparing to the payload. So we're saving about 1.23x in terms of hardware capacity. The number of payload storage access is reduced because, again, of the fact that we don't store the 0 payload of A, and we incur 2 extra metadata storage overhead. But this cost is pretty light comparing to payload storage overhead because of the fact that we only have 2 bits for A coordinates. Of course, if you have a really heavy metadata, you will have different results here. But here we're using a pretty light metadata, 2 bits.